what we want is that the magnitude should decrease of the changes, that is. So we'll just have, so a sub n plus 1 upon a sub n, that's going to be equal to, so it's I1 n plus 1 is just iota over there upon, so we got 3n plus 2, so it's 3 times of n plus 1 over there, so it's like 3n plus 5, and on top you just got, so it's squared actually, so squared, and then you got 3n plus 2 squared. That makes sense. So what we really want is just the magnitude of this stuff, so it's n plus 1 upon even the magnitude of that, that's going to be equal to just the square of this thing, right? So it's just 3n plus 2 square upon 3n plus 5 square, which you can rewrite by dividing by n. So this just becomes, it's like divide by 3n, or even divide by 3n plus 2, that's better. So just 1 upon, so you got 1 plus 3 upon 3n plus 2. That's amazing. So we know that this thing is going to go to infinity as n tends to infinity. So this thing goes to 0. So your ratio approaches 1, but it is still less than 1. The problem with this thing though is that since it approaches 1, your series is actually not going to be convergent. So your series does not converge. That's the problem. This is kind of weird because we know that 1 by n square is actually a convergent series. So these two should technically converge. Why is it not converging in that case? So you got I power n, so it changes constantly. If this was something like 1 upon 3n plus 2 squared, well, we know it converges, right? Yeah, in fact it does converge. So why did we not get that in the ratio? So let's try to do it with this series. You got a sub n equal to 1 upon n square. We know that the summation of 1 upon n square is going to be like pi square by 6, but let's try to see if this actually is going to converge. So we'll just have a sub n plus 1 upon a sub n, that's going to be equal to n square upon n plus 1 square. We know that this thing is actually less than 1 all the time, no big deal, but then the limit as n tends to infinity, this thing approaches 1. So your ratio is approaching 1, sure, and yet your series is a little weird thing. Yeah, I mean it should technically go down all the time, but it isn't going down. That's weird. That's really weird. Yeah. In fact, we know that this series must converge. So, wait, so what is the ratio test exactly? How do you exactly use it? Well, we know that if the ratio is going to be less than 1, then we are pretty much done, but still, just for the sake of it. Right, it's calculus 2 on that. Right, so we usually makes use of this limit. So if L is less than 1, it converges. If L is bigger than 1, say it diverges. So if L equal to 1, you have two things. So if L equal to 1, all the way between spaces in the test is inconclusive because there exists both convergent and divergent. So in this case particularly, you can see that L is in fact equal to 1. In that case, we don't know much, pretty much. So for example, consider the 1 upon n square, right? So this is equal to 1, so this is when L equal to 1, this series may converge or diverge. Makes sense. So now what do you have? You can't say anything, right? So L equal to 1, and so we don't know much. Like, no idea, right? So now what do you do? Well, you have to do some other trickery to get this thing. So we know that the summation of 1 upon n square equal to 1 to infinity, that thing is equal to pi square by 6, right? Therefore this series, so the magnitude of this thing, summation of n equal to 1 to infinity of pi power n upon 3n plus 2 squared, right? This is strictly less, strictly in fact, because some of these are going to be like whatever. So this is in fact, okay, you know what, let's just call it like this. This is less than or equal to this summation from 1 to infinity, sure, which we know is left. So this is like, yeah, you can even make this 1 because it's just I power n in the end. It's just 3n plus 2 squared, nothing big. But then this is strictly less than 1 upon n squared, right? Since only things of a particular form are there, which we know is actually a finite value. So what does this mean? This means that this series magnitude is less than pi squared by 6 all the time. And we also know that this is more or less an increasing series. Consider this. So you start off at some n which has what? Residue 0. Yeah, I shouldn't use residue, although that's what they use. So 0 remainder when divided by 4. So basically n of the form 4k. So what we have, we just have I power 4k, which is like 1. So 1 upon, and then you got 4k over there, so it's just 12k plus 2 square. Then you'll have this thing. So you got 4k plus 1. So you have a extra 3 over there. So 5. Right. Yeah, you get the thing, right? So it's going to be minus and then value minus iota. So it's plus 3, that's 11. Right, something like that. But now notice this. Yeah, notice this. You have this thing and this thing. You combine these two together, what do you get? You know that that's going to be a positive quantity, because this one is a bigger quantity than this. It's a lesser value thing. I mean, this whole thing, right? Similarly over here, we know this is going to be a positive quantity. So in the end, its real part as well as the imaginary part for this series is positive, and it's increasing, right? It increases every time you increment n by 4. So what does that imply? It implies that this is an increasing series. I mean, a weekly sort of increasing series. I don't know. So this series you can similarly write like this. You write it as summation from k equal to 0 to infinity, and it wouldn't make any difference. Yeah. So at k equal to 0, you just have that. Okay. Yeah. Okay. Then you subtract whatever is the 0 term, which is just 1 upon 2 squared. So 1 upon 4. You want to subtract that. But other than that, it's just this series. So now what do you know? You know that this series is actually like an increasing series. At the same time, it's bounded, so it converges. So question number 2. Question number 2 is find the radius of convergence of the following power series. So you've got z minus I power n upon n. We're going to find the radius of convergence. Sure, no big deal. The same thing. You have just the power test, right? So a sub n plus 1 upon a sub n, that's going to be less than 1, and it will be done. So that's going to be something like z minus. So z is a fixed quantity, right? So z minus iota thing to the power of n plus 1. So that cancels. And then the denominator we got n plus 1. Yeah, n over here. So limit as n tends to infinity. This thing is just going to be z minus I, just like that. So what should happen is that this thing should be less than 1. Yeah, as long as that happens, we're good to go. Like, no big deal. So when does this happen? This just happens when z is, oh right, this is the magnitude of that. Sorry for that. Z minus I is less than 1. That's just, this thing is iota over there. This thing is less than 1. So it's just this whole disk. That's it. That's what this radius of convergence is. So basically the radius is 1. It's about ROC, and so the radius of convergence is in fact just 1. No, that's just the first part. The second part is similarly radius of convergence for this thing, so it's n 5 plus 2 iota power n upon 3 power n, whatever. So the same thing, z minus 1, and then you got 3 power n plus 1, that's going to be 3 over there. That's also another fixed constant, so it's 5 plus 2 iota. Yeah, yeah, right. And then you got n plus 1 upon n. So we know that this thing goes to 1. And what about this thing? I mean, we actually want the magnitude of this stuff. So that's going to be magnitude of z minus 1. And then you got this guy's magnitude. So this is 3. This thing is 25 plus 4 is 29. And that is less than 1. That's what we require. So it just means this quantity. So our radius is just that. Pretty straightforward so far. Nothing too complicated. Find a linear expansion of this thing about points z not equal to 1. Okay, cool. So just as before, what we usually do is like we break it. So yeah, whatever. Say this stuff. Yeah, whatever. So this just becomes so we're gonna have a minus z naught and a plus z naught. So that's just 1. So minus 1 plus 1 is like 9. 9 plus z naught minus 1. Yes, let's call this, and this is to the power of negative 1 by 2. Let's call this thing as, I don't know, sorry, it's supposed to be z minus z naught. Let's call that thing as something, x. Yeah. So this just becomes, so this is not the real part that we usually refer to. It's something different. So this just becomes 1 plus x by 9 to the power of negative 1 by 2. That 9 comes outside, so it's just 3 to the power of negative 1. It's 1 by 3. But this we can actually expand, right? And we can expand it whenever you have x by 9 less than 1, right? So when magnitude of x by 9, or more like whenever magnitude of x is less than 9, sorry, we have our function, so f, this is going to be equal to 1/3, and then you got this stuff, so it's just 1 minus 1 by 2 x by 9. I'm just gonna write like x directly this point, z minus z naught by 9. Then you got z minus 1 by 2, right? So yeah, that's just the way to do it. So it's plus, you got 1 by 2, and then you actually subtract 1, so it's negative 1 by 2 minus 1 is like 3 by 2, something like that. Yeah, so you do n minus 1 and then upon 2. Right. This whole thing is now squared, plus so on. So it's just, that's one is going to be negative 1 by 2, 3 by 2, 5 by 2 upon 3 factorial, so that's like 3 times of 2, whatever. Yeah. So you get the thing. Next one's going to be like 4 factorial, but the 4 won't be there. And it just keeps going like that. So this is our Taylor expansion, pretty much. Yeah. About the point. So when is this going to be valid? That's a very good question. When is this going to be valid? This only happens in this very region, wherever your z is like close, you can do this thing, right? Otherwise you cannot. Yeah, this makes sense. For the Laurent expansion, you require it to be like above a certain thing, so that you can do, I mean, it is already having, okay, not exactly, it's 1 negative 1 by 2 power, that's still not a good enough thing to, so yeah, you can't still expand it right away. That sucks. Yeah, that's fine, not a big deal. Okay, next. Find the first 4 terms that is expansion of sin z upon 1 plus sin z about the point z not equal to 1. So yeah, what's sin z? Sin z is just e power I z minus e power negative I z, that upon, is this a valid way to be doing it? Let's see how tau this is going to work. Yeah, let's figure it out. 2 iota over here. is okay. Oh, I see where we're going with this. Oh, this is nice. This is negative. It makes sense. It makes perfect sense. So this is e power I z minus e power negative I z. The denominator is slightly different than what you would usually expect. So what's happening is this is e power, so that 2i cancels. It's e power I z. So here you're gonna have plus 2i, right? So I'm gonna write it as plus 2 e power I z times iota e power negative I z. Yeah, or let's just say z by 2, and then you'll just have negative, so or more like plus iota square e power negative I z by 2 times 2, something like that. You get it what I'm trying to do. So it's just e power I z minus e power negative I z, right? And this we can actually factorize as well. So this is amazing. This is just going to be like e power I z by 2 minus, not even minus, it's plus iota e power yeah, it's going to plus iota, right? I guess so. That actually makes sense. Sure. Right, plus iota e power negative I z by 2, that thing squared. Yes, that's what this thing is. What about this one? Can you factorize it? Something like that? Yeah, that's not going to be happening right away. So 1 plus I z thing we can actually convert. No big deal with that. And then you can probably take it forward, and yeah, that makes sense. But still, the main point is how do you find a Taylor expansion? There's one way to take a derivative and all that, but I don't want to do that. I don't want to take a derivative. That's not going to be very nice. All the points are not equal to 1, huh? Interesting. So not equal to 1. So you're gonna have sine of 1 or something. That's not a very nice thing to do. What happens when z not is equal to 1? The e power iota and e power negative iota. That's just the imaginary part which is left. Yeah, nothing much, nothing bad happens. Wait, okay, we just want to find the first 4 terms. We don't really care about other stuff. So then you can actually just directly use the derivative. No big deal. So there's no Laurent expansion or anything, it's just a simple Taylor expansion. So all you're gonna do is just you can just write f of z is equal to f of z naught plus f dash of z naught naught plus f double dash z naught, or 2 factorial is 2 basically, z minus z naught square. And then so all you really have to do is just figure out these things, f dash, f double dash, f triple dash. Okay, z naught is just equal to 1. Now f dash of z naught, so f dash of z is going to be like derivative of this thing. So firstly, what is f of z? Let's write it in simple term. So f of z you can write, so there's plus 1 minus 1 thing, so this is going to be like 1 minus of 1 upon 1 plus sine z. Alright, so then f dash of z, you can use the derivative rules. So just, this is actually very well defined. It's not a problem with this. So it's going to be 1 upon 1 plus sine z squared, and then this guy's derivative, which is like cosine z. That makes sense. What about f double dash of z? So just have minus 2 cosine z cubed. Sure. This is fine. Yeah, so what we really want is that z equal to 1. What are these values going to be? So you just have a sub 0 equal to whatever f sub, so whatever this thing is. So it's just going to be like sine 1 upon 1. So just 1 minus 1, you just put it directly. So it's sine 1 upon 1 plus sine 1. We just have a1. So we don't know what this value is, but it's something. It's going to be cosine 1 upon 1 plus sine 1 squared, your a sub 2 will just be, so similarly you will just get a derivative, so just minus 2 cosine 1 upon 1 plus sine 1 cube minus sine 1 upon 1 plus sine 1 square. Oh, okay, cool. And then you just get f triple dash as well. What's that gonna be? That's gonna be, just take a derivative of this thing, so just minus 2, so minus 1 plus 2 sine upon the sine cube. Alright, this guy's derivative is just gonna be like minus cosine plus sine squared. Yes, so whatever this thing is gonna be, so that's our a sub 3. And I don't want to figure out what this value is. I'll just leave it like that. Cool, that's question number 4. Question number 5 is, so it's supposed to be z not equal to 1. That's why I've figured it out that z not equal to 1. Okay, so 5 is expand this thing as Lorentz series of z not equal to 0. Yeah, e power 1 z, isn't it? Sure. So you can certainly write it like, that's probably not a good idea. A double summation, that's a bad idea. Come on, think about it. Okay, so this is basically what? This is just something like, just, summation of z power n upon n factorial, and then you got z power negative n upon n factorial, or you could just use m over there as well. Yeah, right. That's what this thing is. So of course this works at any scenario. This works for like for whatever z you have. This similarly works for whatever z you have. Either your region of convergence is pretty much the whole complex plane except z equal to 0, where this thing is undefined, right? So then z power negative doesn't make any sense. But yeah, so that sort of scenario you just have to combine these terms somehow. So your a sub, I don't know, whatever power you want, a sub k. So how do you get the kth power? Well, first you start with, let's think about it. Yeah, it's something like a convolution. So it's z power, so it's gonna be like, I don't know, n, and then z power, so you're gonna subtract n and then add the k, so it's minus of minus k or something like that. This is from n equal to negative infinity to infinity. Actually no, it starts at n equal to, it's not 1, it's 0, right? So it's gonna be 0 to infinity. So like for the 0th power you would require this thing, but then okay, that's actually not gonna be there. Oh, it will be there in fact. Sure. Who says it won't be there? Right, so what we really mean is something like a sub n and b sub n minus k. Yeah. So that the subtraction turns out to be that. Okay, that's weird, but that's just the way it is. This is upon n factorial and n factorial. N is more like n minus k factorial. Interesting. So that's going to be something like, so if I add a k factorial on the top, this just becomes something like 1 by k factorial, and then summation from n equal to 0 to infinity. We just got n choose k, a sub n, b sub n minus k. But what are a sub n and b sub n minus k? 1, pretty much all the time. Yeah. This actually starts from n equal to 0. So it's more like, it's gonna actually start at n equal to k, right? So it's from n equal to k all the way till, well, not infinity precisely. Wait, or is it infinity? It is infinity. Yeah. Now it's just like n choose k. Then you got 1. That's it. So what is this like? It's n choose k and n choose plus 1 choose k, etc. So we know that by Pascal's identity, this thing turns out to be n plus 1 choose k plus 1. Right. Wait, did I mess up something? Why does it look fishy over here? If from n plus 1 people you choose k plus 1 people, then either you could not have me, in which case you just have n people from which you're going to choose k people, or you could have me, in which case you still want to choose k people, but oh sorry, oh no, the correct identity is this thing, sorry for that. So it's n choose k plus 1 plus n choose k, that's going to be n plus 1 choose k plus 1, right? Yeah, so if you don't have me, you have less people but the same amount to select. And if you do have me, you have, oof, okay, this one is also bad. This is how it's supposed to be. Yes, that's more like it. Interesting. So all you gotta do is just add this term first. So you know that you're gonna start at n equal to k, right? So it's gonna be something like k choose k. Now, and the next one is gonna be like k plus 1 choose k. So k choose k is the same thing as k plus 1 choose k as well. Choose k plus 1. So combine these two. What that gives you is k plus 2 choose k plus 1, and then okay, it cascades because k plus 2 choose k is there, so it becomes k plus 3 choose k plus 1, and so on. So eventually this just becomes, let's say it goes till some capital N, right? Then this will be just 1 upon k factorial. You got limit as n tends to infinity of n choose, yeah, essentially that way, isn't it? It sure is. So just n choose k plus 1. Yes, that makes sense. So that's going to be something like that. So as n tends to infinity, yeah, it's gonna explode. This isn't going good at all. No, something is wrong. Something is really wrong about this. Yeah, something isn't quite right. When can you actually expand it like this? Well, actually everywhere, right? It's an exponential, it doesn't really matter. Okay, so like 1 minus 1, so you can't have negatives. Okay, what the hell? So let's just think about the zeroth coefficient. What's gonna happen? You'll have the z power 0, what is it? 1 power 0 factorial, and you have 0 factorial. There you have plus 1, and then you have minus 1, then you have plus 2 and minus 2, and so on. And so this just becomes a problem, really. This isn't good. Oh shit, okay, I get it. I made some really bad mistakes. It's not supposed to be n choose k. It's k choose n. That's more like it. Okay, just delete all that, forget about it completely. And of course, yeah, so at n equal to 0, your b sub n minus k is gonna be 0, right? Your b, yeah, so you can start off at k fit. N equal to k to infinity, k choose n. So we know that n equal, that at n equal to, what the hell, k should be bigger, but then what the, no, this doesn't make any sense. You sure that's n minus k? Well, yes, it has to be. has to be at least k for it to work, right? Okay. So you do start off at k. Okay. This is in fact what you said. No, that would be if it is k minus n, but it's n minus k over there. This is completely different. I don't know what I was dreaming on. But it's this series. Okay, cool. Sure. So this is just going to be the summation of n equal to k to infinity. Yes, it's just 1 and 1 over there. So just 1 upon n factorial minus k. So now how do I even change this? Like, this is something which I've never seen. Minus k factorial. Hey, what the hell? Can you do something with it? No, you can't, right? You subtract, you add and just get like 2n minus k. Not good. This is not good. I'm just gonna leave it like that. That's probably the only thing we can do. So like, let's consider a k equal to 0. What do you get? You just get something like, you know, you get something like summation of 1 upon n factorial squared or something. Something like n equal to 0 to infinity. And yes, this thing is actually increasing at a very fast rate, so we know that, I mean, this is increasing much faster than n squared, so this is actually going to be convergent. No problem with that. Yeah, the convergence isn't a problem, but you don't have a closed form. I was thinking you would actually have a closed form, but fine, whatever. So that's question number 5 for you. Question number 6. Question number 6 is wait, okay, this was question 6. No, question 6 is different. So find a Laurent expansion of f equal to 1 upon z squared plus 1 squared in the largest possible circle about the point z equal to I, and the expression around the origin for mod z not bigger than 1. Okay. Oh shit, okay, if mod z not is bigger than 1, you can't just expand it the usual way, then it doesn't work. Oh, but you can do one thing. So around origin, since we just want a Laurent expansion again, we'll write it like f is equal to, so you take the z outside, so it just becomes z power negative 4 upon 1 plus z power negative 2 squared, but then this is, we know how to do it, z power negative 4, and then you got so 1 then minus 2, so this is negative 2, right? It's negative 2 z power negative 2. Yeah, that makes sense. So this is in the Laurent expansion. Then plus, so you're gonna have like minus 2 minus 1 is like 2 times of 3, but that upon 2 factorial, so it cancels stuff, so it's just plus 3. That makes sense. Sure, that makes sense. So plus 3 z power negative 4 plus, so plus, it's minus 5, because I'm gonna have plus 1 is like 4. Oh shit, 4. So 4 z power negative 6, yeah, plus 5 z power negative 10. So you get the drift. It's just k z power negative 2k negative 1 power k plus 1, pretty much. Yeah, it's an odd number and you don't have the thing, so it's just summation of that. And then add to that 4, so it just becomes minus 4 over there. So this would be the thing, summation of that. Let's start from k equal to 0, right? Yeah, 0 to infinity. No, wait, something's not right. It's minus 2 over there. Oh, it's got to start at k equal to 1, isn't it? Yeah. It actually doesn't matter, but whatever. Just start with k equal to 1. Okay, that's amazing. So that's your f around origin. Somehow with a bit of ingenuity you got it. Okay, that's around origin. Then what else do you want? And you also want this thing there's quite a bit actually, isn't it? Right, the largest possible circle around the point z not equal to I. Okay, largest possible circle about the point z not equal to I. So just not log n exponential. I shouldn't do hard because you can factorize this thing, right? Yeah, so let's just say like z equal to some iota plus, or you know what, scrap that, we'll do it. Yeah, that's fine, you can do it too. Okay, so let's just say iota plus t or something like that. So your f just becomes something like 1 upon, so this just is iota plus t, so it's going to be like negative 1 plus 2 iota t plus t square, and plus 1 over this cancels, you just get this thing, and this whole thing is like squared now, so it's just 1 upon t square, and then you got what, 2 iota plus t to the power of negative 2. Sure, so you can actually even take a 2 iota outside, it just becomes negative 4, so it's negative 1 by 4 t square, and it's this stuff. But that is just negative iota upon 2 times of t. That's better, right? And this is very much doable. This is negative 1 upon 4 t square, and you just got like summation of, so k equal to 1 to infinity, and you don't even have the negative stuff, right? You don't care about that anymore. Yeah, it's supposed to be negative 2 over there, but you get the thing, right? That since that is also alternating, you don't care about it. So it's k equal to 1 to infinity, then you have getting a feeling that something is messed up in the last one. Yes. I see. So when this was like 2, it was negative. K equal to 1 over there. K equal to 0, that is a, yeah. It's actually for 0 you have, yeah, okay, let's just do it the right way. It's k equal to 0 to something. So for 0 it's something like, yes, you just have 1 over there, so it's gonna be k plus 1. Like for z equal to 1 you had 2, right? There was an alternating thing, and this works. Yeah, sure. So similarly you'll have to do it for this one. So there's no alternating thing this time, because obviously this also alternates, but you'll just have ti squared upon 2 squared, right? That's the problem. So but yeah, it's just starting from k equal to 0 to infinity, you will have negative 1 power. Okay, that's actually not there, so just have k plus 1 and this thing, so z power, so it's more like z minus z naught times iota upon 2. So we'll put that later on, but that is the power of negative 2k, and then just have iota power why did I put a negative 2 over there? No, this is supposed to be positive, right? It says t power, yeah. No, that was because it was z1 negative 2 over there. That makes sense. Here it's not the same thing. Here what we have is we took the t outside, so it's fine, right? It's just the thing, ti by 2, that's whatever power you want. So z minus z naught, or z naught is just iota over here, so z minus iota to the power of k, yes, the negative 1, negative iota by 2 to the power of k. Well, not negative, it's just iota by 2 to the power of k. That's better. So okay, now you want to figure out when this is convergent. So yeah, 1 upon, so negative 1 upon 4 t square over here, doesn't matter. This thing is outside in any case, so that's not a problem. This converges when this series can be broken like that. So basically what you want is that the magnitude of t by 2 pretty much that, so since that's just how it's increasing, yeah, every single time it increases like that is going to be less than 1. If this happens, you're good to go, which is to say that magnitude of z minus iota should be less than 2, so its radius is 2. That makes sense. Then you want to figure out the residue. Okay, that's actually the 8th question. We'll come to that later. First figure out the 7. So the 7 is identify the singularities of the following functions. So this is cosine h of z minus 1. So cosine h is actually a very easy function to take. But yeah, so when z equal to 0, okay, that's a 0. That's a 0 only. What is z square? Everywhere else it's not going to have similarity. It's like perfectly differentiable. But when z becomes 0 is the problem. So basically just figure out whether or not z equal to 0 is a similarity. So cosine h of z, that's just like e power z plus e power negative z upon 2, right? So it's going to be plus 2 plus e power negative z. You got 2z square. So this just becomes plus a minus 1, so minus 2 only. This just becomes like e power z by 2 minus e power negative z by 2. Yeah, square upon 2z square. So you can take the z square inside. So it's just this stuff upon z. Yes, that's amazing. Taylor expansion, that's probably the only thing you can do. So does this approach a limit or what? I mean, you can rewrite it as we don't even know if it's going to be singularity, but if there was a singularity, right, its Laurent expansion around that thing would be something like this, right? It would be like 1 plus, like, you know, z by 2, z by 2 square, etc. Whatever, doesn't matter. Some sign stuff going on over there. Okay, and then subtract it, so just 1 minus and subtract it out. So what do you get? You get like 2z by 2 is z plus that stuff, so that cancels out. So you've got 3 factorial z by 2, or 3 by 3 factorial, you got what, 2 times of that, and etc. Right? And that thing upon z. So just like 1 plus, so something like that. So z tends to 0. You know, this actually approaches something nice. Yeah, we know it actually has a Taylor expansion. So if anything, it would be something like a removable singularity. But that's right, it's not actually defined at z equal to 0. So it's a removable singularity because its Taylor expansion exists. Okay, cool. Second is you got f z equal to sin h z upon z power 5. So sin h of z now. Yeah, if z equal to 0, it's still gonna be a problematic thing, but is it removable? So sin h of z is like e power I z. So sorry, not I z. It's e power z minus e power negative z, that upon 2 z power 5, right? But then you can expand this thing to get, so subtract that, right? Yeah, sure. So you just have like 2z. In fact, everything's going to be like 2, 2, 2, but what is it precisely? It's just z plus z cube upon 3 factorial, etc. So this upon z power 5, you'll see that it actually has a residue. This is 1 upon z power 4 plus 1 upon z square. Then you also have the 3 factorial thing. You got 5 factorial, just has 1. Okay, it doesn't have a residue, sure. But still, this is not a Taylor expansion, so it's not a removable singularity, it's a pole. So pole at z equal to 0. Pole of order 4, in fact. Alright, third is z e power 1 upon, once again at z equal to 0 is undefined, so it's some sort of singularity, but what is it like? Well, yeah, this is an essential singularity. I can just say like right away, because e power z is expanded, right? So essential at z equal to 0. Cool. So to the next one. Find the residue of this thing. So we just actually had the thing, right? We had this. So at z equal to iota. So essentially what we want is like whatever is at t equal to 1 thing over there. So that's gonna happen when you have k equal to 1. So just like 2 times of iota upon k, so I'm out of 2 power 1, so it's just like that 2 cancels, just iota. So it's iota times negative 1 upon 4 t square. So that t square is actually used to just negative iota upon 4. That's what we're looking for. So it's just negative iota upon 4. That's your residue because it's the coefficient of t power negative 1, right? Okay, question number 9. We can even try doing it some other way. So we can think of this. You know what? Never mind. Question number. Let's just do it another way. So we can factorize this as z plus iota and z minus iota, or more like iota minus z, then iota plus z. All of these are gonna have like negative 2 powers. So it's square whatever. So you can take iota outside. So it's just gonna be like a negative 1, something like that, and it's just 1 upon iota is like negative iota. So it's just 1 plus iota z power of negative 2. That's also negative 1, so it doesn't really matter. And it's just 1 minus iota z power of negative 2, something like that. Which is pretty obvious, like you can always write it like that. So what does it mean? This means you can actually expand this. It's just like 1 minus 2 iota z why is it having a Taylor expansion? Wait, what the hell? No, this isn't right. So this is actually not correct way to expand it. You are doing it on the origin, so that's not what you want. You want it to be about that thing, right? So yeah, consider this one in fact, or let's actually consider this one. So you can also write it as negative. Turns out you probably are better off writing it again. So just t over there. So it's the same as whatever we wrote before. It's not gonna make any difference, it seems. Question number 9. Test for a pole of order n and calculation of residue at a pole. If z0 is a removable singularity of a complex function, then the necessary and sufficient condition for it to have a pole of order n at z0 is that the limit as it tends to z0, okay, removable singularity of complex function. Necessary sufficient condition is that the limit depends on z0 power n power of, okay. Basically just try to convert it to Taylor series. Wait, this is very weird. If z0 is a removable singularity of a complex function f of z, then a necessary sufficient condition for it to have a pole of order n at z0. How does that even make sense? What the hell? No, how does that even make sense? Okay, this is a typo. It's not a removable singularity, it's just a singularity, right? In most cases, when z0 is a pole of order of f of z, it is much simpler to determine the residue at z0 by one of these formula. Suppose f is g by h has a simple pole at z0. So So these are two analytic functions, so you can completely forget about G pretty much. Right, it has a simple pole at Z0, and G and H are analytic in the neighborhood of Z0. Consider following cases. If H of Z0 equal to 0 and H of Z is equal to Z minus Z0 times F of Z minus okay, that's also analytic. Sure, so in that case, like whatever G is expanded to, since whatever 1 upon Z minus Z0 thing it will have, it just gets cancelled right away. Yeah. What about the case when you have a square thing? Oh, okay, so wait, H is the denominator. Okay, cool. So F is analytic at Z0. This is Z0. And it's not equal to 0. Okay. So yeah, that makes sense. H is in fact analytic, and in that case, it's just like 1 upon Z minus Z0 times some H thing. So that's just something like whatever H of Z0 is upon Z minus Z0 plus some other stuff, which is all non-negative powers. So then the Laurent expansion is pretty easy, and you can easily find the residue. Sure. So you could have used the same thing for the last one, right? Since you had a Z minus Z0 thing, and then there was a Z plus Z0, which doesn't make any difference. So you could have simply figured out whatever the constant value is. So just set Z to be equal to Z0, and then you're done. You could have easily figured out the residue, just like that. Okay, so actually let's try it out. So our thing was 1 plus Z squared plus 1 squared. So that's going to be something like 1 plus Z minus iota, Z plus iota, square, right? So yes, you will have a constant, and then so basically you want the second power, the second term of this thing. Yeah, right. So the one with equal to 1 over there. So you just want to take a derivative of this, and then yeah, just evaluate it as Z0. So this is our H. This whole thing is our H. Oh, sorry. Yeah, it is. Yes. So what you want is like H dash of Z0, or H dash of iota, if you will. So it's gonna be like negative 1 upon, so negative 2 upon Z plus iota squared, and then this thing's derivative is just 1. Okay, and then you want this at iota, so just negative 2 upon 2 iota squared. It's gonna be like negative 4 iota. Yeah, just negative 4. So it's gonna be like just 1 by 2. Did I do this correctly or what? Sure, that's a negative. I mean, it should be. It definitely should be. So it's supposed to be 1 by 2 at the. Messed up. Sure. This is a negative iota by 4, unfortunately, by this logic. Must have messed up something. Sure, this is correct. I mean, it seems correct. So then why did it get something like that? It's supposed to be at iota. So you just want the 1 power thing. Yes. And we know that's just going to be that, right? Negative 2. Oh shit, it's a cube. It's a cube over there. Okay, that makes sense. So it's not this thing. It's instead negative 8 iota. So that's actually going to be negative iota by 4. So just iota by 4, in fact. Sorry, 1 upon 4 iota. So that's negative iota by 4. Which is, yeah, it's exactly the same thing. So fine, that works. So let's go to 9th. What do you want to do? It is it's simply to determine the residue by one of the okay, sure, that's one way. Right. Okay, so that's just the proof. Similarly, H of Z0 equal to 0. But so what do you want to do in A? So let's say h of z naught is in fact 0, but h cannot be returned as this thing. Then f will have a Laurent expansion of this form. H is analytic. H is analytic. But you can't write it as a minus z naught times f. Every analytic function has a Taylor expansion. Z naught is a 0 of h. Huh? What can happen? The only thing is like f can be a constant function. That's pretty much it, right? Yeah. The residue of f is z naught, and then what the hell? H dash of z naught. Wait, this is very weird. So you're saying f is like, you can't write it like that. Why? It can't be written like that. What it is certainly 0 over there. Okay, it does not invalidate that theorem that every analytic function does have like a 0 somewhere. Yeah, it sure does. But this is still weird. Even though it has a 0, you can't write it like that. You can't use the derivative to get it. It cannot be done like that. Why? We don't know. But anyway, just move on. So let's just say f is g by h, and that's the residue. Okay, that's just like by definition. So if it has a Laurent expansion, we can do this. So it's just residue of f at z naught upon z minus z naught. That's this summation. This from 0 to infinity. So there are no other powers involved. There's no negative or anything. Gotta think about it. Previously it was something like, yeah. So I think there are like multiple ways of doing the Laurent expansion. That's probably the only same thing that we can conclude from this. Right, but then all of them should give us the same thing because we just have the residue thing going on. Cool. So all you are really saying is that f should be constant. There's no other way that this can actually happen, right? Because we know this is a Taylor expandable thing, so we can always factorize it. Yes, that's right. That's perfectly right. Yep, you can write a Taylor expansion around z naught. That's the thing. So in that case, your f is just like all the terms which have z minus z naught to power something bigger than 0, right? And that divided by z minus z naught, obviously. But yes, because your constant term is just 0. So since it cannot be written like that, where f is some sort of analytic function, the only sensible, wait, it is analytic somewhere, is analytic everywhere. That's the thing, right? So f is in fact an analytic function. So what are they suggesting? It must be that f is 1. Yeah, that f is 1 or some constant or something like that. Okay, got it. So you're quite literally saying that h is some constant times z minus z naught. That's the only thing that can be happening, because I haven't seen a function like that. Cool. In that case, it makes sense. You just Taylor expand G and then you get this thing. Amazing. Therefore, the residue of f at z naught, that's just the limit as z tends to z naught. So you got G upon H multiplied by z naught, obviously, yeah. And that's cool, that's cool. The reason you can take this sort of a limit is because there are no other terms in Laurent expansion. So basically it's pole of order 1 or something like that. Now using h of z not equal to 0, you can write okay, yeah, fine by me, this makes sense. Right, so for pole of order 1 you can always do this sort of thing, that makes sense. Cool. So suppose f has a pole of order n at z naught. The Laurent expansion of f over z naught is of this form, so there's n minus 1 over there. Okay, that's a bit bizarre. What the hell? Oh, okay, it's z minus z naught for n, and then there's an n minus 1. A minus 1. Okay, that is fine. So this a minus 1, right? That makes sense. Yeah, some other stuff, positive stuff, we don't care about it. After differentiate with respect to z, we get, okay, cool. So that's gonna be another constant which just clears out. Amazing. So taking limit as that tends to, so that's just another Taylor thing. Sure, we get, okay, some 1 minus n. That's amazing. Sure. Something really fishy is going on, but okay, the constant that will be left is something like that. Okay, so successively differentiating it n minus 1 times, we get a minus 1 is 1 upon n minus 1 factorial. So what do you want to do with that? Oh, okay, you're getting the residue somehow. Okay, so what you're trying to do is something like, I see, so multiply by whatever is the lowest power, then take a derivative, right? Yeah. In fact, okay, you're just taking a bunch of derivatives, like the nth derivative or something like that. Sure. And that definitely gives this thing, no problem with that. A minus 1. Yeah. Since I just literally divided by that, so it's gonna be the thing. It's like n minus 1 of that, so it's just n minus factorial comes out. No big deal. That's just like this z minus z naught power n f is like an analytic function, and yeah, this is pretty much just describing the coefficient for the n minus 1 term. So yeah, okay, let's get to it. Find the residue of the poles in following functions. Residue at poles. So this has a pole at iota, right? I think that's the only singularity it has. So let's go. And let's do it by these two different methods. So first you want to write it as some sort of analytic function that times something else. So you can write it as g upon h, where h is of the form z minus iota times 1, right? So it falls into that thing. So then what do you do? Well, okay, that's gonna have some particular expansion, you have some constant terms, whatever, we don't really care. And that's just it. So all you gotta do is just figure out what is this value at z equal to iota. That's it. That's all you really have to do, huh? So whatever Taylor expansion you have, you just add z minus iota power negative 1 over there. Multiply, it's more like it. So what method are we going for in that case? Your h is something like, h is the same as g in fact, which is z squared plus 2z plus 3, right? You have written your h thing as z minus z naught times something, so f of z, where f is analytic. It happens to be 1 in fact. Then you're expanding it like that, so in that case your residue is just your h thing at z naught. Yeah, so just h of z naught. Amazing. So what does it mean? H of z naught is equal to residue, which is, just put iota over there, just minus 1 plus 2 iota plus 3, so just 2 plus 2 iota. Cool. It's pretty easy. Question number 2 is, so okay, the same thing as before, just the same thing, precisely the same thing. So you can once again rewrite it like this thing, just like z plus iota times z minus iota to the power of -2, -2. So this is of the form, how do I even say this? So we know it's gonna have like an order 2 pole at z equal to iota, right? Yeah, because this function times z minus iota power 2, that happens to be a analytic function, so it's definitely an order 2 thing. So then what do you do? How do you find the z equal to 1, so z equal to, sorry, the minus 1 power term, right? So you can use this thing, you can use the residue of f and z, that's going to be just multiply by z minus z naught power n. Sure, n is 2, so it just happens to be 1 upon z plus iota power -2. Take the n minus 1th derivative, so n is 2, that minus 1 is like 1, so take the first derivative, that first derivative upon 1 factorial, okay, evaluated at z naught obviously, that's going to be a residue. Cool. So let's just call this something like z minus z naught power n f, let's call it like some capital F. So capital F is just something like 1 upon z plus iota power -2, so f dash, that's going to be like minus 2 upon z plus iota power -3. This is exactly what we did, in fact. Yes. And yeah, so what we require is like f dash upon 1 factorial evaluated at z naught. So z naught is just iota, so it's going to be like -2 upon 2 iota or -3, sorry, to the power of 3. Wait, what? Oh, it's supposed to be square root. sorry for that. It's not like that. Okay, so this is going to be like -2 upon 8 iota negative, right, which is just 1 upon 4 iota, which is like negative iota by 4. So that's a residue. Simple. Okay, so that's this way. Any other thing that you could have done? You could have written it like this, so your h would just be like that, and in that case you just have to get, yeah, sure. So okay, you could have written like this, where f is, okay, no, but it's square over there, you can't do it like that. You have to go to the order n thing. Yeah, okay, whatever. Third is 1 upon z sine z, so it's z equal to 0 is messed up. Yep, this is messed up. You kind of know it's gonna be an order 2 thing, but how do I prove that? Well, how do you prove it? The order is, so suppose it has a pole of order n. How do you know it's a pole of order n? Well, you can just prove that, like, if I multiply by z square, which is order 2 over here, so z square, then this function just becomes like capital F equal to, so capital F is just like z square f, that's gonna be like z upon sine z. So if I can just prove that this guy's, so we know it's gonna be at 0, so if this guy's derivative is multiple derivatives, right, all derivatives in fact, at z equal to 0 are, heck, that's not the way to prove it. We'll have to prove that this actually has a Taylor expansion. This is analytic. Oh wait, so you just have to prove that this actually has a derivative, right? This function has a derivative, and then it just becomes some sort of a, so then you would have removed that singularity, isn't that right? Yeah, this function actually has a removable singularity, z square f, which has a removable singularity at z equal to 0, because its extension, when you fill up all the dots, this has a complex derivative at z equal to 0, so it will be done. How do you prove this actually has a complex derivative? The first thing, continuity. So it is continuous because the limit as z tends to 0 of z upon sine z is equal to 1, right? How do I say that? Like, so blindly you can think of it as x y approaching 0, and this just becomes like something like x plus I y upon, this is some stupid thing actually, sine of zeta. So with real values it would have worked like right away. If you approach it on the x-axis, this would have makes sense, sure. But what about the imaginary values? We'll see. So it's e power iota z minus e power negative iota z upon 2 iota. So yeah, get it. I'll expand that thing. That's always like e power iota x involved as well. So if y equal to 0, it makes sense, the partial derivative stuff. But if like x equal to 0 and you're changing y, this just becomes something like, so as an iota y, just negative y is the iota goes up, so like negative 2 y upon e power iota y, sorry, y. Oh wait, sorry, it's iota z, right? So just, yeah. Cool. So it's e power iota. No, it's not even an iota anymore. So it's negative y minus. Right, which happens to be something like y upon sine h of y. And so yeah, this is like 0 by 0 situation. So by using L'Hopital's rule, this is like 1 upon cosine h of y, which is in fact 1. So yes, it's partial. So if you like approach it from one way and the other way, both of these do exist. That's not the problem. But how do you actually prove it's continuous? You don't have a way of doing that, do you? No, it seems not. Heck, forget that. How do you even prove that this is actually differentiable? Well, you can use a classic approach. It will just be like z upon sine z minus 0 by 0. So assuming that the limit exists and it's like 1, that's the thing, upon z. Yeah. So that's something like z minus sine z upon z sine z or something like that. Right. That's even more complicated. This is not going good. We have no way of figuring out whether or not this is actually a good thing. We know that sine z is an analytic function, but like what about 1 upon sine z? We don't know. So we have to figure out some other way to do it. So you can fit it into that sense that you have a f and g and yeah, right. So h, so g and h, okay, and h is like z minus z naught times something analytic. So capital F just happens to be sine z. So in that sort of scenario, you just have h is 1 upon sine z. That's going to be, oh wait, but that requires your h to not be like 0. Right. F is analytic and it's at the same time not equal to 0. That isn't happening. This really sucks, doesn't it? Come on, think about it. What's the conjugate over there? No. Doesn't work. It just doesn't work like that. What can I do about this? Okay, so let's actually figure out what this limit is. Whether or not it's even continuous is now the main doubt. So we want to prove that. So first let's actually try to do this limit instead. Sine z upon z. Is this going to be continuous? Right? The usual sinc function limit. So you can rewrite this as e power iota z minus e power. So let's just say z is like x plus iy. Then this is going to be like x plus iy over there. And this one is going to be like e power x, e power iy minus e power, that would be sine h, not, so you got an iota x, right? E power negative y, e power iota x minus e power y, e power negative iota x. You got 2 iota over there, right? This is so stupid. How am I gonna do this? I think the better way to be doing this is something like this. What you can do is you write this as yeah 1 minus e power sub 2 iota. It's just negative 2, negative iota by 2, and then it's gonna take the negative one outside, right? Yeah. And then this times of e power negative iota. That's better. Now this thing approaches 0, we know that for sure. What about this? This stuff. Well, this is in the end just e power iota, so it's 2 iota like x over there. Something like this. Sure, the partial derivatives are the same. So partial, limits, I don't know what to call it. They sure are the same. That's not the problem. The question really is if you approach it from some other way, will it actually be the same, right? Yeah. R2 continuity is not just so easy, right? It's not just like you approach it in one way or some other way. You're done. No. You have to approach it in all different ways. And then if it doesn't work, then it's not continuous. So how do you prove it's continuous? Come on, there's got to be some way. Bounding it? That's one way. I highly doubt that's actually gonna work, but sure. There's gonna be some way. You can rewrite like this thing. So e power 2y minus e power 2ix. That's sure. Then I'm not getting anything after that. This is not making sense. You want to prove this is equal to 1. In that case, what I want to do is just this minus 1. I want to say that, oh well, if x plus iy is like less than some delta value, or if it's like deviating by delta, in that case, this is still bounded by some epsilon. Right? For every epsilon, there will be existing some delta, so that this can happen. Yeah. This is just so weird. I don't think this is gonna happen. Yeah, I have zero idea how to actually prove this limit. How do you even find a residue? This is some stupid thing. 1 by sine z. What the? Do I just assume that this has like some sort of a Taylor expansion and just be done with it? I can do that, no big deal. And then I know in that case I can just do it pretty easily. Let's just assume that your h is something like z upon, so h is something like z minus z naught, so z square in fact times fz. That is just z upon sine z. This is analytic, I just assume that. In that case I can differentiate this, so then h dash would just be like, so since we just want to figure out the first power here, right? So since it's order 2, do that, differentiate it, and that's the thing. So h dash will be something like this is already looking bad. I don't know what's happening. This isn't going good at all. Like, what the hell? There's some Taylor expansion stuff that you'll have to do now. It's not even approximately, just have to write it at this point. Oh, this is so bad. This is just disgusting. It's got set square over there, sure. It's like what, 1 plus z cube upon, not even 1 plus, it's something like, starts off with z. So z cube upon 3 factorial plus z power 5 upon 5 factorial, etc. Minus the tensor cosine, minus plus factorial, etc. stuff. So you subtract that upon sine square z. So like what, we cancel that out, and then it's got plus z cube upon 2 factorial, so just 6 over there is z cube upon 6 and other stuff. So then that's upon sine square of z, and so yeah, this is higher powers. So sure, so this is actually gonna approach 0, which is okay, so this is gonna approach 0, so then this limit should be 0, right? So then the residue is 0. That's messed up. Residue is being 0. Unexpected. Wait, is it unexpected that the residue is 0? No, it's not. It actually isn't, because I can prove it. So how do you get the residue? You get the residue by doing the integration, right? So the integration over c sub r, so in this case it's just 0 in any case, right? So c sub r 1 upon z sine z dz, right? So 0, that is. Now since this is an even function, yeah, you get what I'm getting. Yep. So firstly you can write it in the proper parameterized way. It's integration from t equal to 0 to 2 pi of 1 upon, so it's just e power I, right? So that cancels, just sine of e power I t. That's interesting. Precisely all the negative values are there, right? I see. Since sine is a negative function, you can actually break it. Okay, that's just how it is. But then you can break it from pi to 2 pi, and then so the pi to 2 pi thing, you can, let's say pi plus, right, so you can set z equal to be pi plus z, right? Or e to be pi plus t or something like that. Then e power I pi is -1, so sine of -1 times e power I t, so that is negative over there. Amazing. But then dt is also negative. Wait, it's pi plus 2 over there, so just no, okay, that's not gonna happen. But yeah, it's negative, but it's the same integral, so it cancels out. So this residue is in fact 0. So just by basic evaluation, you can say that residue is 0, and it just so works out. It actually works out pretty nice. That's amazing. So yes, the residue is 0, and I'm still not sure if it's an analytic function, but yeah, the third one is true. Just by simple calculation, you can see that the residue is in fact 0, just because it was like a doable thing. Okay, this is cool. So you solved this tutorial. Wasn't there like an assignment or something? That's assignment 1. This is tutorial 3, 2, 1, whatever. I just need more questions at this point. So this tutorial something. Okay, let's try to do it. So the ratio test, so from this ratio test, this convergence, blah blah, this limit 1, the ratio test fails. Yeah, convergent series 1 by n square, compare it with that. Series is absolutely convergent. Okay, that's kind of a nice thing. It's actually convergent, isn't it? We just differentiate or whatever, which is okay. You can write it as another series with all 4 terms, different iota powers combined together, and then that series is actually absolutely convergent. This seems fine. Find the radius of convergence of the series. Yeah, just r equal to 1. What's the big deal? What were you expecting? Yeah, that's just 1. Then find the Taylor expansion of this at z not equal to 1. So yeah, the usual stuff. Okay, why is it not 54u? What the hell? 1 by 3 minus 1 by 54. I don't think that's correct. No, you don't Taylor expand it like that. No. Just no. This isn't quite correct. The 54, let's try it out. So it's like take the 1 by 3 outside of this, it's like negative 1 upon what? 18. So is that gonna be 18? 1 by 2, 3 by 2. Subtract 1, right? Into factorial is 2, pretty much. So it's gonna be like 3 by 8. Where did 18 come from? I don't think this is the series. Okay, you know what? So this should happen at least for real values, right? Yes. So I'm going to open Desmos and then we'll see what's the deal. Oops. Wrong. Hey, why is it doing that? This is also gonna work. Okay. Graphing calculator. I do not think this is correct. So what you want is just this 1 by 3. Then you got 1 plus. I don't think it even works for real values. Square root of that. Yeah, whatever. Let's try it out. So it's 1 by 3. It's 1 by 54. Oops, this is not how it's supposed to be. Minus, so it's just z minus 1 upon 54. Then 1 by 648 minus 1 square. Okay, I should put x what I've not said. Why is it so close to it? Is it really the expansion? That can't be. Why would it be like this? Oh, there's a 9 over there. Okay, that makes sense. Then sure you would have that. Okay, I messed up somewhere. It's 2 factorial over there. It's gonna be like. Okay. Sure. Wait, so just to be sure, what you actually have is like there's a 1 by 3 involved. Okay. Then you got u square and stuff. So there's a 9. Something is going really weird around this, but who cares? So just u by 9 conjugated, right? So it's just okay, just 1 by 9 power negative. I mean negative just 1 power 1. Okay, since it's u over there, then you got 1 by 2, 1 by 3. 1 by 2, 2 by 3, 7. So this just becomes 8. Which is, yeah, I mean it's, wait, what? No, it's 8, right? So it should be 72. Where did I mess up? Why is it 54 over there? What the hell? It's not -1 or anything. -54 of all things. There's an extra. What the hell? Should be an extra 2 over there or something like that. 3 by 2, 2 factorial. It's as if you multiply by 2. No, this is wrong, right? 54. That's like 9 times of 6. And that's definitely not this thing. How? How did you get that? Come on, think about it. Think about it. Nearly 1 by 2. You don't do a plus. That's not what you do. Definitely not. You just do a minus, right? All the time. Yeah, like n minus 1, so on. Is it really a thing? I don't believe it. Why is it fitting so good? Okay, the 640 is at -1 squared. Let's keep going. So -5 by this number, 5 by, you can't copy it, okay. 5 by 3, 4, 9, 9, 2. This really is converging, isn't it? It's supposed to converge at z equal to 1 the most. But okay, that's not happening. Wait, what? This is supposed to be exactly the same at z equal to 1. Oh, it's x minus 1 over here. Sorry for that. Oh, what happened? Is it there or not? Okay, it's exactly converging. Something weird happened. Why is this actually working when it should not be working? What the hell? Why? Why did this work? It's 2 factorial over there and it's gonna be 8 times. It's just impossible, right? It's 27 over there. What could have happened to push it like that? You can't possibly doing like 2 by 1. That's just impossible. 54. Okay, I don't know. I'll look into it. Fine. I don't think this is a right expansion, but okay, I'll go ahead with it. Yeah, I definitely don't think this is the right expansion. Hey, let's try figuring it out with the derivatives. So 8 plus z power negative, so negative 1 by 2, take a derivative of that. It's negative 1 by 2, then you got 8 plus z to the power of 3 by 2, and then you just got 1. And so we want this at z equal to, so yeah, z equal to 1, right? It's going to be like negative 1 by 2, and then you got 8 power 3 by 2, sure. Then this is going to be actually having 1 upon 2 factorial. Oh, it's supposed to be 9 power 3 by 2. That's negative 1 upon 4 times 8. What? Why did this happen? Okay. That's 3 cubed, that's 27. Yes, they are right. This is actually just 6 times of 9, but why? Why was my thing failing? Why did that happen? Can't we just use binomial expansion? I mean, what you essentially have is just 1 plus u to the e by 9 to the power of negative 1 by 2, right? Yeah, 1/3 of that, of course. But it's gonna be like 1/3 short and then plus the other one. So just negative 1 by 2. Why was I putting a square? Why was I putting a square in there? Okay, I get it. I get what went wrong. Just negative 1 by 2, that comes up. And then you got like just a 1 factorial. Yeah, you just got u by 9. It's 1 by 9 and you got u. Cool. And yes, this is just 9 times of 6, which is true. Okay, something weird happened. I don't know. It's doing something weird. But yeah, so the balance series converges for u less than 9 and z minus 1 less than 9. Yes. Fine. This is okay. Just produce the same thing. Then you gotta expand f as a Lorentz series among z not equal to 0. Sure. So a sub 0 is just 1 plus 1. Okay, so on. So it's 1 upon k factorial square. The okay. So a sub 1 you have the same thing. And in general, what do you have? Wait, what did they do? Sub minus 1 is this thing. Oh, this is just the usual Lorentz expansion thing. I didn't actually find the normal thing, right? The, what do we call it? The coefficients as a function. They didn't find it, but fine. Two. Okay. Interesting. Hey, so this isn't the complete story. What should also happen is that this should be able, we should be able to expand this, right? Using whatever formula we have. And you can only do that if, right? Think about it. What the hell? There's a 2 order, isn't it? This is 1 upon 0 minus 1. Okay, cool. So this is actually fine. Because they're putting minus iota over there. It's fine, it's fine, it's fine. The other guy over there. How did they come up with this directly? I don't know. If iota minus iota equal to 2. I know what they're doing. You know, they're adding minus iota and subtracting minus iota, and then just saying that only for z, factor of z less than the other one should this actually happen. I get that, but still very weird. Fine. Okay, what about this one? Order expansion of f is equal to 1 plus. Obviously, we did this. So what did they get? This Lorentz expansion. It's this thing. Negative iota upon 4, sure. Minus 1 upon 4 is administered. So mine expansion was something like this, right? Yeah. So yeah, sure. Negative iota by 4 thing I get. No problem with that, huh? Okay. Then at z at k equal to 1, we'll just have. So you've got negative 1 by 4, and then you have. Shit, okay, that was actually k equal to 1 itself. Yes, it seems. So you want k equal to 2, right? So that's going to be like 3, and then you got. Iota power 3 is like negative iota. Negative cancel, it's just iota. Just 3 by what? Just k over here, it's just going to be 2. So just 4. So got 3 by 4, then negative iota, and then just negative 1 by 4 of that. Yes. So then you just have basically like 3 iota upon 16. And what did they write? I can't see what they wrote. Oh, they just have negative 1 by 4. Why? I don't get it. Yeah, don't get it. It's gotta be 3, right? Am I really just doing something weird about this? It's gotta be minus 2 over there. No, it is supposed to be 3. N plus 3 about n. Okay, I believe in that. Equal to 0 to infinity. Square. Oh shit, okay, this is not that. It's actually the 0 term. It's when k equal to 0. When k equal to 0, what do you get? You just get like 1. And then this isn't there at all. It's just negative 1 by 4. Okay, this is fine. They are about the same thing. I was really starting to think that maybe I'm just doing something insane. Okay, this is fine. Never mind that. Okay, let's. So for inside you have an expansion, and for outside you too have an expansion. Interesting. See, we're trying to do it around the origin, right? Yeah. Where you? Where did you try to do it around the origin? Sure, where? When like z is less than 1, you can definitely do it like right away. When z is bigger than 1, yeah, some weird thing. When z is equal to 1, there are problems. Okay, so you have two things. One is that z less than 1, you can do that. Z bigger than 1, you can do that. And then whatever. order 2, sure. We had the same thing, right? I had an order 4 thing. Wait, this is some other thing going on. I don't think this is in question 7. Okay, that's just one of the parts. Where are the other parts? Not put that there. Okay, fine, whatever. Now we're going for question number 8, so it's negative iota by 4. Cool. It has an order 2 pole. Fine. Question 9. That's 2 times 1 plus iota. Sure. Negative iota by 4. It's supposed to be negative iota by 4, since it's the same function completely. Yeah. Yep, it's the same function. We know it's residue. It has a pole, so it's at a pole of order 2. Then let's attend to iota of this thing. You want the 1 by z. Oh, it's taking derivative for that. Sure. Okay. Let's see what I negative 1 by 4. Okay, cool. I somehow don't believe you, because we know that residue is not 1 by 4, it's negative iota by 4. But fine, do whatever you want to. I don't know what these people are doing. So residue at z not equal to iota, and z not equal to negative iota. Written it's like negative 1 by 4 and iota by 4, which is wrong. We know it's gonna be like negative iota by 4 because the residue over there was that. Right, at z equal to iota. How can you contradict yourself? These are the same functions, right? Yep. Some weird thing going on. Oh, okay. You also probably should find the residue at a different location, right? At the z equal to negative iota thing. So that just happens to be the inverse of it, but okay. Hey, why is that the case? Symmetry makes sense. Okay, then you had this complicated thing, 1 by z sine z. So then you just Taylor expanded, therefore it has a pole of order 2. It's not equal to 0. How can you say it so blatantly? How can you be so sure? Oh, because this thing is square by 2 factorial, z power 4 upon 5 factorial, so on. Interesting. Still, so are you sure this will never be actually equal to 0? It will be, right? Like, consider z equal to pi. At that point, this will be in fact 0. So how are you so sure about it? At z equal to 0, this thing will not be 0. So it's analytic over there. I see. Because this function is analytic. And so this 1 upon this function is also analytic. I see. Oh, that was a pretty simple argument. Why couldn't I think of that? Still, writing as a Taylor expansion and then doing it is just not going good. Probably because it's absolutely convergent, so you can do stuff, but still. Okay. So you got that. Okay, so residue at these differences. Oh, so when they say find residue, they mean find all the residues. See, so nowhere else will the 1 by z have a limit. Yeah. Z not equal to, so I get at z equal to plus or minus n pi. You can, okay, by sine z plus cosine, what the hell just happened? Yeah, f is something like this, 1 upon sine z plus z cosine z. What? Why did you write it like that? You had z sine z and then you took a derivative. You took a derivative, didn't you? You see, why did you do it like that? Why? What did you do to write like that? What the hell? Seriously, what the hell is this? Think about it. Okay, I think I have another way to do it. Probably not the best way, but let's try it out. This becomes 1 upon z plus n pi. Then sine of, or more like z minus n pi plus n pi. So let's call this as t plus n pi. The sine of t plus n pi, but then that just becomes negative 1 power n sine t. Sure. We can have a residue of that. Okay, this you can Taylor expand. I see. You just basically, it just boils down to 1 upon sine t, integrating that essentially. It's like integrating. So yeah, since I'm just using the definition pretty much, I shouldn't call it t. I should just call it z at this point. Yeah, so that thing 1 upon z, that's actually analytic, so you can let it go outside, and it's not approaching 0 or anything, so it's a different story altogether. Okay, in that case, 1 by sine z, it has some residue. You just want to figure that out. I see. Sure, that makes sense. Right. So it just boils down to find the residue of, oh, but we already know, how to Taylor expand 1 by z sine z. Yeah, so you can write it, the sine z as well, you can write it as 1 upon z minus all that stuff. So this just turns out to be something like 1 upon z times of 1 upon 1 minus z square by 2, etc. So at z equal to 0, this thing would be something like, so this whole thing would be more or less analytic. So your residue is pretty much just take the derivative of this stuff. You don't even take the derivative, just set z to be equal to 0. So it's just 1 by z, pretty much. So the residue will be 1 for sine, 1 upon sine z. But then you have, yeah, so that n pi thing over there. So it's like 1 by n pi upon n pi. Yes, makes sense. So yeah, that's actually correct. Yes, this is correct. I get it. So now it's assignment 2. So assignment 1, tutorial 1, whatever. Lecture notes. I guess we'll just read lecture notes at this point. Or maybe I should just take a break.